Good morning, everyone. We will start the third lecture of Raghu Mahajan from Stanford. And if you have any question during the lecture, don't hesitate to ask any question. It's okay. So please welcome.
Okay. Okay. All right. Thank you, Ishangi. Yeah. Let's just recap where we were at the end of last time. So we were trying to derive a page curve for a non-evaporating black hole or an eternal black hole. And the setup we had was an ADS black hole coupled to flat space, which on the field theory side means we have an SYK model, which is responsible for creating an ADS2 black hole coupled to a heat bath, which we take to be a wire living on the positive real axis. And this system is in thermal equilibrium. So we introduce its purification, the standard purification that makes the system into a thermophile double. And we defined our radiation region to be a piece of the wire on the right and its partner on the left. So this is the blue region is the region A. And we have defined our time evolution state as e to the negative it, the left Hamiltonian plus the right Hamiltonian acting on the thermophile double state. So this defines some time-dependent state. And we were asking for the entropy S of A as a function of time. What was this? And last time, we said that this curve should have an initial piece which is linearly growing in time. That's captures the initial Hawking radiation. Or in terms of condensed matter or just quantum mechanical language, this captures the fact that the thermophile double state is a quenched high energy state from the point of view of the Hamiltonian H left plus H right. But we also said that this growth cannot continue forever because the region A complement has a finite dimensional Hilbert space, and that has a finite fixed entropy. So this curve has to transition into something flat at some point. Last time we computed the curve 1, and we found that SA at early time went like C over 3 log 2 cosh of 2 pi t over beta. And essentially for times up to much greater than beta, this is C over 3 times 2 pi t over beta. So it's linear in time with a coefficient proportional to C. Okay, and then we started trying to compute the second curve, this phase 2 here. And for that, we said the quantum extremal surface, etc., is going to be important. And we wrote down the relevant JT gravity solution. So the relevant JT gravity solution, the metric has some Weyl factor times just a standard flat space, where omega was sinh. Sorry, I used y here, dy plus dy minus 2 pi over beta times negative y times beta over 2 pi. And then our dilaton had a profile which was also some trigonometric function, but it was caught hyperbolic, 2 pi over beta negative y times beta over 2 pi. Let me just check. Sorry, I got this wrong. This is 2 pi over beta. And remember that y goes to 0, the solution looks just like the 0 temperature solution. The omega looks like y and is the boundary, is the UV boundary. And phi looks like 1 over y. Okay, so with this, we needed one more result, which is S matter in the thermal state. So as a function of beta and in the interval A to B. we computed last time was equal to C over 3 log of beta over pi times sinh of B minus A times pi over beta. Okay, so now we are just going to use all these results and compute where the island lies, what's the entanglement wedge of the radiation, and also compute the final value of the entropy. Okay, so let's get started. But again, we need to solve a simpler problem first because this it still has too many pieces, and we need to solve just one simple problem, which is the following. So, oh, I should pause here because this was a review from last time. Are there any questions about what we did last time? Okay, let's continue then. So what we will do is we will simplify our lives first and just compute the quantum extremal surface corresponding to just one of these SYK dots. So nothing else. Our region A, we will now take to be just this right dot. So the region from 0 to B. Okay, this is the system, and we are asking what is its entanglement wedge. Where does the QES lie? Okay, so let's draw the Penrose diagram. We have ADS2, we have the Rindler patch, and we have these flat space regions. So again, this is ADS, this is flat, this is flat. We have this point here. Let me call this point P. So we have the point P with coordinate B, and its quantum extremal surface will lie somewhere here, right? We will just have some candidate quantum extremal surface Q. And this will be the entanglement wedge. Okay, so now we're just supposed to find what are the coordinates of Q. Okay, so let's just, we have to construct the entropy functional. So again, we begin by just writing down the coordinates. So P and Q. So in the T comma Y coordinate, P, we are taking to have coordinate 0 comma B. So it's at 0 time and spatial coordinate B. And Q, we will take to have 0 comma negative A. I'm just putting a minus sign so that this quantity A turns out to be positive. And remember that Y is a coordinate that increases this way. Y is equal to 0 here. Okay, all right, so this is easy. We have done everything we need. So what's Sgen? Sgen is a function of A, right? It's the point Q that we are bearing, so we need to find this A. And this is equal to the dilaton at A plus S matter. Sorry, it's minus A between minus A and B, right? That's the definition. And this is just equal to phi R. And now we use the dilaton from before. So the dilaton had a 2 pi over beta and a hyperbolic cotangent. So it's equal to 2 pi over beta, hyperbolic cotangent 2 pi A over beta. Okay, S matter. So this is what's the state of the matter field? It's a thermal state at temperature beta. So to compute the entropy, if it was flat space, if PQ was completely flat, we would have the entropy given here. Okay, so we can write that. So we have plus C over 3 log beta over pi sinh of B plus A, right? Pi over beta is just B plus A because I took the coordinate here to be negative A. So the difference in the spatial coordinates is B plus A. But we have to remember that we have ADS here, not flat space. So there is a correction coming from, again, the Weil factor. So it's minus C over 6 log of omega, but we know what omega is. Omega we wrote above, it's sinh of 2 pi A over beta, beta over 2 pi. Okay, so that's it. So we have written down our generalized entropy functional as a function of A. And all we need to do now is take a derivative with respect to A and set it to 0. So I will spare you the algebra. It's pretty simple. But so let me write down the final equation that you get in a nice way. The equation that would determine the A star. So the equation that determines it is phi r times 2 pi over beta, 1 over sinh 2 pi. Let me just call it A star now. So this is the minimization value equals C over 6 sinh pi over beta A minus B over sinh pi over beta A plus B. Okay, A star, A star. So this is the equation that determines A star. And okay, it's a little bit complicated. You can't write it down immediately. So in order to analyze what the physical content is, let's try to understand some limits. So limits. The first limit we can take is a temperature equals 0, which is the same as beta equals infinity with B equals 0. It's just what we did before, what we did in the first lecture. Okay, so let's see. So on the left-hand side, we don't get anything. We just get, well, the sinh simplifies, right? So since beta is very large, the argument of the sinh is small. So we just get 1 over A star equals. And since we are taking B to be 0, the right-hand side is just C over 6. Okay, so we recover the A star we found at 0 temperature. It was simply phi r, which sets the length scale, and then 6 over C. Okay, so this looks good. Okay, but we don't want to be at 0 temperature. We really, want to understand some finite temperature physics, and so what's going on. So the other limit we can take. Let me move this. Below here and go back. Okay, so what's the physics? I want to say that there is a limit which is phi r over beta much larger than C. What is this physically saying? Remember that the entropy of the black hole in this model is phi naught plus phi r over beta. It's linear in the temperature, and there was some 2 pi here. So phi r over beta is a measure of how much entropy the black hole has above extremality. And what this condition limit star is saying is that in each time step, the black hole entropy doesn't reduce by that much if it was evaporating. Because we have C number of matter fields. C is like how many scalar fields we have, like how many fields are causing the black hole to evaporate. If C was comparable to the entropy of the black hole, that would mean that the black hole is going to disappear very, very quickly. Like we don't have some nice big black hole which is adiabatically shrinking very slowly. So this is what this means. So this is a nice limit, a physical limit to consider, where the evaporation time scale is much larger than beta. That's what it means. And this is what we do have in real life. So that's just a motivation thing, but we can do this. And again, to simplify our lives, B doesn't really play any role. So we can also set B to 0 and B to 0. B to 0 just defines what region we are considering, right? So our point P could have been all the way just at the SYK dot. So that's all that means. Okay, so what does the equation become? We get phi r times 2 pi over beta times 1 over sinh 2 pi A star over beta equals C over 6, right? But because of the condition star, the way to satisfy this equation is if A star is very large, right? Because phi r is large, C is small, so the cinch needs to be large in order to compensate that. So that says that we can basically replace the cinch by an exponential. It's 2 times e to the negative 2 pi A star over beta equals C over 6. So we just collect stuff. We have phi r over beta times 24 pi times 1 over C equals e to the 2 pi A star over beta. Okay, I'll have to move this further down. And basically what this says is that A star equals beta over 2 pi log of 24 pi, it's not important, phi r over beta divided by C. Okay, now, okay, so this is the position of the quantum extremal surface. And this position determines the point Q such that QP is the entanglement wedge of the single SYK system on the right-hand side. What is the physical meaning of this quantity, what we have obtained here? So let me rewrite this. I will ignore some overall constants. We have here S minus S naught, right? S is the entropy of the black hole because it was proportional to phi r over beta. It was linear in the temperature divided by C. And this is nothing but the scrambling time. The scrambling time of any black hole is equal to beta times log of the entropy. Usually you might have seen it with S naught equals 0. People usually discuss it for non-extremal black holes. But this is its generalization for extremal black holes. And we have a C here, usually C is equal to 1. We don't have any too many matter fields flying around. Okay, so this is the value. So what we learn is that if we take B to 0, if P is, let me just draw this again, move below here. We have this wedge, and what we learned is that if we take B to 0, we have a point Q here, and this is the entanglement wedge of the SYK with the point Q having coordinate A star, which was having coordinate negative A star, which is A star equals the scrambling time or the scrambling position time. Yeah. So what does this mean physically? Why did it have to come out to be the scrambling time like this? Okay, so for that, again, whenever we have to get intuition, we go back to the SYK system. So here, let me just draw here the SYK system coupled to a wire. There is, of course, the thermofield partner here. And we were looking at some entanglement wedge of this region. So what does it mean? Imagine that you threw in an excitation at this point. Imagine that we insert an excitation little e sometime in the past. It follows some light-like trajectory in the bulk, right? What it says is that if you make this excitation e in the SYK, after a scrambling time, it will no longer be recoverable from just the SYK degrees of freedom, because it will go past the point Q near the horizon, and that region belongs to the wire, or it belongs to the union of the wire and the other side. So this makes sense because in a fast scrambling system, we lose access to simple degrees of freedom in a time of order the scrambling time. So a simple excitation made a scrambling time in the past will leak out of the system after evolving for a scrambling time. So that's a physical argument for why the scrambling time shows up, and we see it come out here from extremizing the generalized entropy. Okay, so this is the end of the toy problem. or the lemma that we wanted to prove. Is there any question about this?
Yeah, I have a quick question and just a very fundamental confusion. Yeah. Could you scroll down to the figure that you just draw?
Yeah.
This one. So why is it this diamond? I mean, the rays from Q, why are they not going all the way hitting the boundary?
Oh, because we have the point P here, right?
Right, but the vertical is T, vertical is time. I mean, think of the entanglement wedge runs. So the spatial slice P to Q, but then you have the light rays from Q that would go all the way to boundary. Why does it end? So I'm confused about this. It should just be.
I think maybe it's because so there is no light rays on the boundary here, right? There is only time.
Yes, but I'm talking about the light rays that the light cone from Q, the red line that goes from Q, that's null line, that should just keep going. Why does it?
Well, it's the light cone, right? If we just have some interval, it's the domain of dependence of PQ. It's like you can ask the same question if you're in Minkowski space and you have an interval. Like, what is its domain of dependence?
Well,
we draw this light cone and we draw this.
Yes, that is clear to me. For Minkowski, it's clear, but for entanglement wedge, it really is a wedge, right? I mean, as time goes on, P keeps moving up, right?
Okay, maybe we can draw it all the way. I would just emphasize that if you draw it like that, then if you insert some operator here, if you change the state, if you chose to change the state at a later time on the boundary by doing something, then it would not be encoded in this region.
So if you were to draw these lines till the boundary, then I would say that would be true if, for example, your E is below that. So from what you have drawn, is E even very close to P? Well, it will register.
I think what you're referring to is, I think it's because there is no transverse dimension here. So why in higher dimensions does the entanglement wedge go all the way to the boundary? Because you have an interval on the boundary, right? I'm thinking out loud, so pardon me if I get this wrong. Mm-hmm. So you have an interval on the boundary and you draw the causal domain of dependence of that point.
At the boundary.
At the boundary, right?
Right, yeah.
But the domain of dependence of this object in a one dimension is just the point itself, right?
It's the whole.
Maybe.
It's the whole time axis.
Okay. Yeah, you can draw. Okay.
Yeah, so I think that's what it should be, but I'm.
Okay, I'm gonna just draw it like this because I'm failing to come up with a response in real time to why that is. But
yeah, that's okay. It's not a major point. I mean, the point you are making is well taken scrambling time, but we can sort it out later.
Yeah.
Thanks.
Okay, thanks. Yeah. Okay, are there any other questions? Okay, all right. If not, then let's move on to do the actual computation that we wanted to do. So now the phase 2 of this object. Yeah. Okay, so again, we have the Penrose diagram. We draw it again and again. And now we have this region A, which is at time t. So our region was the blue region, which goes all the way here. and it goes here at time t. And I've moved them in time because we want to compute it at some time. So this is the point B and the point B. Okay, we are looking for some kind of an island. And from intuition, we know that the island sort of develops in the interior region of the black hole. So maybe, roughly speaking, we expect something like this. We expect like an island region like this. And okay, so now we want to find what's the end point here. Where does this point lie? How do we find the coordinate of this point? The idea is if you assume that it's a minimization procedure. So you can assume something and you can try to see where its derivative vanishes. Let's assume some island like this. Now, what are we computing? We have these 4 endpoints. So now we are actually, if we want to compute the S matter of this blue configuration here, it will be entanglement entropy of 2 intervals in CFD2. The 2 intervals being just the complement of the blue region I have drawn. Okay, but this is not universal. And we can see why it's not universal is again by this twist operator argument. This would be a 4-point function of twist operators. And a 4-point function of twist operators depends on the full spectrum of the CFD2 that you have and the OPE coefficients and so on. So unless I tell you more details about what the matter CFD2 is, you cannot calculate this quantity. But we can use some simplification. Like we saw last time, this point here, let me call this Q and Q tilde. The Q and Q tilde move very far apart, right? As time goes on, these were sort of the points that are following maybe some hyperbolic trajectory, and they go very far away from each other. What this means is that we can compute this 4-point function in an OPE expansion. And the OPE expansion happens between the point P and Q. So there's a twist operator here and a twist operator here. We can fuse them. And we can, again, take the twist operator at P tilde and the twist operator at Q tilde and fuse them. And only keep the first term in the OPE expansion, which is the identity operator. So we just factorize this 4-point function. We don't even do an OPE expansion. We factorize the 4-point function into 2-point functions. And what this means is that the entropy is given by the sum of these 2 intervals. So the entropy, we were computing a 2-interval entanglement entropy, is just equal to the entropy of one interval plus the entropy of the other interval. But then that problem becomes very easy to solve. It's just what we extremized here, right? This was exactly the problem that we solved for one interval on one side. And now the problem has just split into 2 independent problems. Okay, so that's why I went through this sub-problem of computing this A star. So we know that at late times, we've already solved this problem. And up to this argument that I wrote in the text here, that again, the A star is going to be located at beta over 2 pi log of 24 pi phi r over beta over c. So this is the quantum extremal surface. And if we plug that value in, this is the island region here, like that. And the entanglement wedges, again, will be drawn like this. Okay. So again, the side regions, the ones that I already shaded, would be the naive entanglement wedges of the radiation or the causal wedge. And the one that I'm now shading in orange is the non-trivial one. It's like far away from the radiation, close to the horizon. And this is the island. And okay, so we have one last thing left to do, is to actually estimate what the value of the horizontal line is. So what is the entropy of this? And so one thing becomes clear, right? That the entropy is going to be independent of time, because Q and P, now we're just doing a Rindler boost on both of them. So it's going to be a constant in time, because as you move P forwards in time, the point Q sort of moves accordingly. And sort of that's why we had done like a static computation over here. But what is the actual value of the entropy? So to look at the value of the entropy, we just need to look at the functional that we constructed. The functional that we constructed was right here in this example over in this expression over here. And we found that A is pretty big, right? When we had tried to solve this in this limit of slow evaporation, the sinh we had approximated with an exponential because A is large. So when A is large, the coth we can approximate to be 1. And you can check that, so that contributes terms of order phi r over beta. The other two terms you can check contribute only terms of order c times some logarithm. So they're not as big. So basically, even though these latter terms, the second and the third term, were important to cancel the derivatives and set the derivative equal to 0, on the extremum, they don't contribute that much to the value of the entropy. So the entropy is essentially equal to the first term. And A being large means what? That it's very, very close to the horizon, right? And so this quantity here is basically the black hole entropy again. So we see how this new quantum extremal surface is imposing the fact that the value of the generalized entropy is basically equal to the entropy of the black hole, because A is large. It's almost at the horizon. It's a little bit outside the horizon, but it's almost at the horizon. And again, it's this inequality that we make use of. So that immediately tells us that if we go and plot the curve of the entropy as a function of time, we are going to get something like this. Time, and now we can like even put some numbers here. This is going to be S black hole times beta over C. And this is just going to be 2 times S black hole. There's some order 1 number here. And the slope here is C over beta, which is why this page time. Okay, so this is the page time. Okay, so now we have derived all of this. We have finished the derivation, including all the technical details of this eternal page curve. Okay, are there any questions about this? Because now we will transition to, we will take a break from computing all these entropies and taking derivatives, and try to give do a different style of the computation. So this is a good time to maybe ask questions, but I will also just maybe take a break for like 2 minutes or so, just to give people a breather.
So just in this computation, you did not use any replica or anything that.
Yeah.
The calculation.
So, this is like, go on.
So could you comment on?
Comment on that?
Yeah.
Yeah. So it's like, when Ryu and Takeyanagi discussed their formula, they just said find a surface, extremize it, and that was it, right? They didn't say why it was the minimal area surface that's computing the entropy. Right? That was their conjecture.
I see. So you're saying that basically the place where it has gone to is in the basic formula of the quantum extremals.
Exactly.
So replica arguments are hiding in there, but once you have that, then everything just goes through without replica.
Yeah, I was just going to say that. So Lukowitz and Maldacena gave a derivation of the RT formula, going through the Renyi entropy and analytic continuations and so on. So the replica wormholes are basically, if you tried to do what Lukowitz and Maldacena did for these problems, you would find the replica wormholes. Right? So there are these two sides. One is a practical approach. Okay, I just want to apply the formula, apply the root Hakenagi formula, or its souped up version, this QES formula. But what's the derivation? Why is the root Hakenagi, giving the correct answer? And that's like some gravitational path integral that sets up n copies of the system and so on and so forth. So that's on this side. So that's like a derivation of the QES. Right? But when we apply the RT formula, we don't always go to Lukowitz-Maldacena, try to find the saddle points and then analytically continue.
Okay, so all that is contained in the basic formula of entropy that we have.
Yeah.
Right?
Yes.
I-line plus. Okay.
Yeah.
Thanks.
Yeah.
Thanks.
I have a question.
Yes.
So
yeah.
I don't see exactly where the ADS was crucial. Can you maybe pinpoint that?
Well, you're right. The ADS was not really crucial, and people have indeed written papers about just flat space black holes. The only place where ADS is it's like a starting point, because we know that ADS CFT exists, and we know what's the dual of an ADS black hole. It's like this SYK system or some n equals 4 super Yang-Mills, right? And then we say, okay, but ADS black holes don't evaporate, so we can make them evaporate by putting in this wire. So, but if you forget about, in any of these diagrams that I've been drawing, if you forget about these vertical lines, for example, this looks very much like the Penrose diagram of a flat space black hole, right? With some singularities here and so on. So it is actually not important. Like after, you have realized this, you have done these computations, it's not important. And indeed, Jeff Pennington's first paper on this, he worked directly with flat space black holes, and he was not working with this ADS glued to flat space. So we believe that the same formulas are true in higher dimensions and for flat space black holes.
So here the missing point might be the derivation of the QES formula?
Yeah, exactly. Yeah. But I should say that even here, the derivation is a little bit, and Suvrat Raju has emphasized this point, that we know what the holographic dual is of n equals 4 super Yang-Mills. It's ADS5. But do we really fundamentally know that the dual of n equals 4 super Yang-Mills coupled to a bath is just the ADS coupled to a bath, right? That's some good intuition, and it's probably correct, but we don't have a derivation of that. So, if we wiggle our hands, then it makes sort of both of these at roughly the same level of rigor.
Mm-hmm.
So what we want to say is that sort of the strongly gravitating region near the horizon of any black hole can be replaced by an SYK-like system with some finite number of degrees of freedom. And outside you have some wire stuff, like some heat bath.
I see.
Yeah.
Thanks.
So I thought
yes.
Merrill and Maxfield in their paper, Observations of Hawking Radiation, they have,
this is the second paper.
The second paper. Yeah. So they have kind of derived this, right, for the flat space black holes, the island formula? Or you think that's not quite a derivation? I mean, there are some subtle points, and then they have another paper with Rangmani and all where they do variation calculations and so on. But I think it's
yeah. I just don't know. Like the idea is like, the entropies are rigorously defined in some non-gravitational theory. Like that's why I like this SYK coupled to the wire picture, because it's a non-gravitational system where we know how to define entropies. In flat space, the only place where you can define entropies is strictly at Scri+. And the structure of Scri+ is kind of funky. Like it's a lossy system. Like as you grow up, it loses energy and so on. So I'm just not 100% sure, that there's some hidden assumptions there about what the fundamental description is of a flat space black hole. Here, it's sort of the opposite. Here, we know what the boundary system is. It's some bunch of spins coupled to a wire. But we don't for sure 100% know that these pictures we are drawing with ADS and gluing in some flat space region is 100% the dual of the quantum mechanical system. I think the Marolf and Maxfield paper was basically commenting upon how to think about these replica wormholes in Lorentzian signature.
right.
And once you sort of do these basic toy computations and realize what the fundamental physics is, you don't need to take ADS. Like it's clear that the ADS doesn't play much role. What plays a role is the amount of entanglement between sort of this region deep inside and the region outside.
Right. Yeah, there, of course, like you said, it's not that entropy is defined of a, like the boundary system here and the bath. There, it's by entropy, what really means that the entropy as you define using path integral and, del over del beta and so on, or Renier entropy, just from the gravitational path integral.
Yeah, but then the question is, if we define them that way, then what's the proof that those entropies obey all the properties of a von Neumann entropy of a quantum system? Right, that's what the problem would become. Like we can of course define some derivatives on the gravitational path integral, but then you would have to rederive all the nice properties that the quantum information theoretic entropies have.
But they just follow from, if you have a Hilbert space and quantum mechanical system, they follow. So if you're assuming that gravity has that description, that you have a Hilbert space, you have operators, and
right,
and
that's what I said. Like, so that's what you have to assume.
Yeah. Okay. Yeah.
So it's basically the same assumption. Every time you do these computations, you sort of have to assume that near the center of the black hole, near the horizon, you can replace the strongly gravitating region by just some finite number of spins. And then you're in business.
Okay.
Yeah.
Thanks.
Okay. Any more questions? Okay. If not, then maybe let's discuss. We've always been saying that there is this tent shape curve and so on for the entropy, but can we actually compute something? Can we actually do some math that shows this kind of tent shape? And here is a simple model. So page curve. And after this, we will go to the evaporating black hole case, page curve derivation. Well, derivation is in quotes. I will do some simple toy example. So we start with some bipartite system. And we take a state, which is sum over I and alpha, C I alpha, I alpha. Okay, so I could be the black hole system, and I will take it, the index to go from 1 to m. And alpha is maybe the radiation system, and its index goes from 1 to n. And the page curve is a curve about generic states like this. So to make a generic state, let's assume that Ci alpha are drawn independently from a Gaussian with the zero mean and variance sigma squared. Okay, so I just have m times n number of random variables, IID random variables, and I pick them to form the state. Okay, but the state has to be normalized. So norm equals 1 implies that 1 equals sum over I and alpha Ci alpha squared. And now I can take an expectation value of this equation. So that's like sigma squared times mn, right? Each of these. So these states are normalized on average. And if m and n are big, the error we make is small. So this basically gives us a value for sigma. Sigma is mn to the minus a half. So then if we pick the Ci alpha with zero mean and this amount of variance, we get a good model of a random looking state, of a random looking bipartite state where m and n are large and it's normalized. Okay, so let me write the state here again. So we have Ci alpha, I alpha, sum over I and alpha. This is the global state, psi. And we want to trace over, let's say, the radiation system to find what's the entropy of the black hole. So trace over alpha, or the other way around, doesn't matter. Trace over alpha. Now, what's the density matrix? So we have to take psi and psi star and do the trace. So what we will have is Ci alpha, C star, J alpha, sum over alpha, Ij, right? And then there's a sum over I and J outside. So this is our density matrix for the first system. You can see where this is going. We won't actually compute trace rho log rho, but the simplest object that people compute is trace rho squared. This is called the purity, and it's equal to 1 if the state is pure, but it's less than 1 if the state is not pure. And if the state is maximally mixed, it's equal to like 1 over the dimension of the Hilbert. So it's a matter of how mixed the state is. So we can compute this. So we have to take 2 of the rows and then take a trace. So that means we have a sum over alpha, Ci alpha, J alpha star, sum over beta. Now trace rho squared is rho ij, rho ji, right? Sum over I and j. So we have to flip the order of j and I. So j beta, C star, I alpha, right? And there is still a sum over I and j outside. Okay, so how do we compute this? Again, these are Gaussian random variables. We have 2 C's and 2 C stars. So we can compute this using Wick contractions. So there are 2 Wick contractions. One is like this. So this is Wick contraction number 1. And we have this Wick contraction. This is Wick contraction number 2. So what does Wick contraction number 1 give? So there's a sum over ij alpha beta. So it's a delta function, right? So we get sigma squared delta ij. And when we do the Wick contraction 1, we have the other 2. So it's sigma squared delta ji plus the other Wick contraction. So sigma squared delta, this here is beta, delta alpha beta, sigma squared delta alpha beta. Okay, so basically we have a sigma to the 4th outside, right? In the first term, we have a delta ij. And I was going from 1 through m, and alpha and beta go from 1 to n, right? So we're just going to get one sum over I and j. So that gives a factor of m. But the sum over alpha and beta is unrestricted. So we get n squared from the first term. The second term is the opposite. The I and j indices are unrestricted, but the alpha beta constrained to be equal. So it's m squared n. Okay, and I'll remind you above that sigma had some value. It was mn to the minus a half. So sigma to the fourth is mn to the minus 2. So this is equal to mn to the minus 2, mn squared, m squared n, which is equal to m to the minus 1 plus n to the minus 1. So this is a very simple result. Okay, but let's analyze this. So let's say initially, right, at the initial times, when a black hole is mostly large, m is much larger than n. It's mostly black hole and no radiation. And then we expect, just from this formula, the m inverse term is not important at all, and this is n inverse. N, remember, was like the number of states in the radiation. So this is like a maximally mixed state of the radiation. So this is exactly Hawking's result, or something like that, that you have a system which is small and its state is generic. So its purity is equal to n minus 1. And if you had computed trace rho log rho, you would have found log n. Okay, but at the end, you see m is much less than n. And in this formula, you basically keep the larger of the two terms. So that is basically the essence of the page curve. And notice that this is completely symmetric between m and n. So this is why you have a tent shape of the page curve. Is this argument clear? Was this derivation clear? Okay.
Wait, so this
Yes.
assumes unitarity, right? That the system you're describing is unitary.
Well, actually, you see, Page's statement is a statement about. There are two ways to say it. One is a statement about the entanglement structure of typical states in the Hilbert space. So the state that we started with here, the Ci alpha I alpha, is some generic state in the Hilbert space. And the question is just, what is its entanglement dependence on m and n, when m is much smaller than n or m is much less than n? Where unitarity comes in is when you have a black hole evaporating, right? Unitarity says that the total number of degrees of freedom should not change. Like, it's not like we are adding some new degrees of freedom as time evolves. So m plus m times n is fixed, basically. It's the total dimension of the Hilbert space that we started with. If you could just create entropy, like if you could just, add a qubit each time the black hole emits something, you would not have a problem, right?
Could you repeat the last statement, please?
I'm just saying the unitarity comes in because you start with like, m equals 2 to the s black hole, right? And n equals 1. That's the starting point.
Right.
Right. So then you get some entropy, like a log of m, which is s. In the end, because your state is pure, you have m equals 1 and n equals 2 to the s. And the state is still pure. If you didn't have unitarity, the state at the end could have been a mixed state. So you might say that, okay, this state is not a good model anymore because this is a pure state in a state of, in a Hilbert space of dimension m times n. So what you're using is that the state sort of remains pure as a function of time, right? So at each time, all that happens is that the m and n get shuffled around, but the state is still pure. If it was a mixed state, I would have to start with something like I alpha j beta, a c I alpha j beta, right? It would be a much more complicated set of coefficients.
Mm-hmm.
So yeah.
Would you remind me, this test saying that trace rho square is equal to 1 is,
Yeah.
does it not, this, just the,
Trace rho squared equals 1, and then what?
so trace rho equals 1, trace rho square is equal to 1 implies that it's a
The
pure
state is
state.
pure.
Yeah. Does that depend upon unitarity or not? I don't
No,
remember.
that's just a statement about states, right? It's just some state, like the unitarity is a statement about what the Hamiltonian is and how the time dependent.
Dynamic.
This is just a kinematic statement about.
Okay.
Yeah.
Mm-hmm. Okay, thanks.
Okay. And maybe next time we will, actually see how in this paper of Pennington, Saad, not Saad, Pennington, Schenker, Stanford, and Yang, there was a very similar formula with M and N, basically playing the same role. M is the dimension of the black hole, and N is the dimension of some internal states. Radiation. Okay. All right. If there are no more questions, then let's try to, see how these kind of things that we discussed for the eternal black hole we can use to learn about evaporating black holes. So this was just an interlude, this computation, because I think it's a useful one to know, and we will maybe touch upon it next time. But now we are back to a real evaporating black holes. And this will be very qualitative. And it will hopefully supplement the discussion in the other lectures of the black hole information. Okay, so what happens, right? So real black holes form from collapse and evaporate. So we have some shell of matter that comes in, collapses. This is in the Eddington-Finkelstein, forms a singularity, and then there is some horizon that forms, stays here. But what evaporation means is that this horizon is gradually receding, right? It's turning inwards. And actually, if I just erase this stuff here, what the evaporation does is brings the horizon closer and closer and closer to the singularity, and it ends here. There's no more singularity after that. So this is what evaporation does. Closes off the interior region of the black hole, and our observers sort of stay outside. The point is, this process is very slow. The process of the black hole horizon shrinking is a very, very slow process, so that at any sort of instant of time during this evaporation process, we can base proximity locally looks very much like that of just a regular black hole. And this is very important because it makes life simple. Like, okay. Just to emphasize that black hole evaporation is slow. A metric can be taken Okay. I think my internet is lagging, no? Yeah, I'll change it. Sorry, just give me 1 second. Okay, this should be better. Can be taken to be the usual Schwarzschild metric. Okay, with a slowly receding horizon. Okay, so we are going to sort of write down the metric and an ansatz for the generalized entropy, and sort of argue where the QES lies. This is following the original paper of Pennington. These are the arguments there. So here we won't have any ADS or anything like that. It's just flat space black holes. Okay. So let's, instead of drawing the Finkelstein diagram, let's draw the Penrose diagram. There's a singularity. Here's the horizon. Even though it's like a 45-degree line, the horizon is slowly shrinking. So the value of R is smaller and smaller and smaller and smaller as time goes on. And the way we measure time along this horizon is the coordinate little b, the Eddington, the ingoing out. Okay, and here's the black hole. So again, we have to define here a black hole region. So we will try to find the entanglement wedge of the black hole. So let's make a partition here. So whatever is to the left of this partition, we will call the black hole region, and whatever is to the right, we call the radiation, right? Just like before. Okay, so here we have something, and now again, we are trying to find some kind of a quantum extremal surface here, Q and P. So our goal is, given P, we are going to find Q. Okay, and P we are going to take to have a coordinate V equals 0. P will have V equals 0. And Q will end up lying to the past of P, like somewhere here, and somewhat inside the horizon. So up to now, all our quantum extremal surfaces lie outside the horizon. That's because we were in some eternal black hole. Here it actually lies inside. So here's the point Q. Our goal is to find the coordinates of Q. So what is the V coordinate? And what's its R? Like how inside is it? How deep inside the horizon is it? You know, naively, if we were completely naive, we would say that there is no such quantum extremal surface. There is just the R equal to 0 region, and the point Q should be all the way at R equals 0. So this is the R equal to 0 line.
Wait, so in this case, you are minimizing the area of Q plus the entropy of the radiation.
QP. Plus the entropy of matter in QP.
Plus the entropy of matter in QP. Okay, yeah, thanks.
Yeah, so the naive QES would be all the way at the origin, that the black hole interior belongs to the black hole system. You know, the radiation far away doesn't interfere with whatever goes on the inside of the black hole. That would be the original, you know, intuition. But you know, here's something that that would challenge it. And so the really nice thing about this paper of Jeff was that he found a new quantum extremal surface Q that is actually just inside the horizon. It's very close to the horizon, and it's to the past of P. And if the intuition from before is some guide, we expect that the V difference, the time difference, V is basically time, between P and Q is the scrambling time, which is large. It's large by log of 1 over g Newton. So, and it's close near the horizon, okay? So we have to find the equations that give us those results. Okay, so how do we go about doing this? This is a complicated problem. Yes.
Q seems like space-like separated to P. So what do you mean it's in the past of P?
Well, sorry, it is space-like separated. I just mean in this coordinates V and R.
Okay, it's
if
less
the P,
than.
yeah, it's like the delta V between them is like the scrambling time.
Okay.
Sorry. Yeah. It's like before, right? P and Q were space-like, but sort of the coordinate separation was was the scrambling time.
Okay, yeah.
Yeah.
Mhm.
Okay, all right. So we have to find some way of computing the entropy of the matter fields in PQ. At one point, like, you might give up because it's a 4-dimensional black hole. You know, there's a 2-sphere here, and who knows, we don't even know anything about 4-dimensional entropies. But we start to make progress when we realize that most of the Hawking radiation sort of happens in the S-wave modes. So there is a potential barrier for the higher angular momentum modes. So we assume that all the important entanglement comes from the S-wave modes. So we only keep sort of the spherically symmetric configurations. And since we only keep the S-wave mode, the transverse sphere is not important. So actually, again, you can compute entropies using 2D formulas. So that's the idea. So essentially, you are performing a kind of a dimensional reduction again, and you're back to sort of, you know, JT type things. But we will couch it in this language and see how it comes about. So okay, so here's SGen. I'm going to write a formula and then explain it. So there's an area over 4G, right? Plus S matter of PQ. Area is 4 pi r square in 2D. So this is pi over G times r square. Plus, I'm going to write here now. So imagine that the number of S-wave modes that you have in the system forms like a 2-dimensional CFT of central charge C. So C just measures how many degrees of freedom are causing the black hole to evaporate. So it is C over 6 log of U minus U naught plus C over 6 log V and plus C over 12 V. Okay, so little v I have defined as the usual Finkelstein coordinate. It's not the Kruskal one, it's just the usual, you know, t plus r star, where r star is the tortoise coordinate. Capital U, on the other hand, is the Kruskal coordinate. Is the Kruskal U. And that's the U that goes smoothly through this horizon. So the capital U goes like that, where the horizon lying at U equals 0, right? Because we don't have a past horizon, we don't need to worry about capital V. Little v suffices. So the coordinates that we work with are capital U and little v. These are our coordinates. And what's U naught? So the point capital P has V equals 0 and U equals U naught, which is negative. It is negative, it's because it's to the past of the horizon. So the U coordinate, the capital U coordinate there is negative. Okay, and our goal is to find the coordinates of Q. So these two terms look familiar. These are just log of the coordinate separations. And this term here comes from the Weil factor. Again, it's like some kind of cutoff, is because the metric has a non-trivial profile. But what is the actual metric and why do we have this? And why do we pick this funny choice between capital U and little v? Okay, so explaining the cutoff factor is actually easy. So the metric, you know, in Kruskal coordinates is basically d capital U, d capital V plus r squared d omega squared, right? And I'm linearizing near the horizon. So near the horizon, U and V are just like light cone coordinates, but we are not using capital V. So I'm just going to write this as e to the little v times d capital U, d little v. And we're going to forget about the 2-sphere because it's not going to do anything. So you see, this is the metric. This is just the Kruskal metric near the horizon. Okay, so you see here, if we compare this to, so this is not that omega, this is just a 2-sphere. So if we compare to the form we have been writing, you know, we have been writing the metrics as minus omega to the minus 2, dx plus dx minus. This is basically of this form with omega equals e to the negative v over 2. So log omega is negative v over 2 And then we are supposed to multiply it by negative c over 6. So we get cv over 12, which is this term here. So we've explained this term. And the other two terms are also explained if we explain why it's natural to use capital U and the little v coordinate. Okay, so why is that? It's because of the choice of state. So we always assume that when we are working with an evaporating black hole, the natural state is the Unruh state, not the Hartle-Hawking state, not the Bolver state, but the Unruh state. And the point is, the little v coordinate is complete on scry minus. There is no past horizon which comes to interfere with scry minus. So the little v coordinate is a natural coordinate on scry minus, and the quantum fields are in their vacuum. The ingoing fields are in their vacuum just with respect to the v coordinate. And similarly for capital U, right? Because we have a future horizon and not a past horizon, the little u coordinate would be a bad coordinate. It would just end at the future horizon. Like it would be little u equals infinity. But it's the capital Kruskal U that goes smoothly across the horizon. So, the modes that go like that, the right moving modes are sort of in the vacuum with respect to the capital U coordinate. And then, you naturally just explain this u minus u naught, this logarithms here. Just log of delta x plus and log of delta x minus. It's a bit subtle and it's a bit qualitative, and I apologize, but this is this is correct, and it will give us the locations of the quantum extremal surface. So let me write that functional again here. Yes.
Can I ask a question? So can I think of those two terms as basically for the left moving modes and for the right moving modes, just the entanglement entropy of a line? Just think of it as a CFT of an interval. So you get one for left moving, one for right moving, and that's
exactly. So we are computing the entropy of PQ, right? We are computing the entropy of this interval.
Right.
So P and Q we have here, like this gives the V separation, right? That's V.
Mm-hmm.
And then there's the other separation, which is in capital U, right? That's the U minus U naught that I wrote.
Mm-hmm.
Like this separation here. Was that clear? Maybe I should draw this diagram again.
Well, that means what I was saying is not correct.
Sorry? It's the entropy of a line segment. Isn't that what you said?
I said that, but that should just be C/6 log times delta of the line segment. But why are there two of them? That's the question, right?
Well, remember we wrote the formula as, so there's the formula starts out as C/3 log L. We write that as C/6 log of L square, which by Lorentz invariance get written as delta x square minus delta t square. And so in terms of the light cones, it's actually two terms, log of delta x plus and log of delta x minus.
Okay, very clear now. Yeah. Okay.
So it's this difference between the 3 and the 6.
Mm-hmm. Okay.
Okay. All right. So we have this. So we have S gen. What we wrote here was pi over g times r squared plus C/6 log of u minus u naught plus C/6 times v. Log v plus cv over 12. Okay, but there is a relationship between little r and capital U and little v. And that is capital U times e to the little v is capital UV. And this vanishes at the horizon. This is equal to negative of r minus rs times rs, roughly speaking. This is the relationship. Let me just forget about this. Let's emphasize that there's a 0. So u equal to 0 is the horizon. And now we just need to take partial capital U, set it to 0. And we need to take partial little v and set it to 0. Okay, so let me just do that. Let me write the equations here. Okay, I'm just gonna. I haven't written the constant factor here, but I can write it now. It's Rs beta over 2 pi whole squared. And setting beta equals 2 pi. So, okay, so what you will get is pi over g times 2r. That's because we have an r squared. And then there's a partial r over capital U. So that actually gives negative rs times v, big V, equals negative c over 6, 1 over u minus u naught. So this is the u derivative. We have a 1 over u minus u naught from that term. Partial v term gives pi over g times 2r times negative rs times capital U, capital V is negative c over 12. Okay, I have to explain what happens here. What happens is that this term actually does not contribute any derivatives, because when you take the derivative, it becomes 1 over v. And we expect that at the QES, the v is going to be large. So we can check it by self-consistency, because v, remember, is going to be roughly proportional to the scrambling time of that order, and that's large. It's large because there's a log of 1 over g Newton in it. So this minus c over 12 basically comes from this term here, from the ddv of that term. Okay, so there are just these two equations, and the simplest thing to do is to divide them. So when we divide, we will get a value for u. So we get 1 over big U equals 2 over u minus u naught, which means that u minus u naught is 2u, or u star, the location is negative u naught. Okay, so this is the u coordinate of the quantum extremal surface. The minus sign makes sense because u naught was negative, remember, because the point P was to the past of the horizon. So that means that u star is positive. And that means that Q is actually in the interior of the black hole, is to the future of the horizon. So that's the value of capital U. And once we have this, we can see from the second equation what the value of little v is going to be. So capital V is actually e to the little v, right? This is just e to the little v. So e to the little v is of order c over s black hole. So v is of the order negative log of s black hole over c. Why did I write s black hole? Because it's the entropy of the black hole is r squared over g. So we have r squared over g, and that's why it's like an s black hole, factor of s black hole, and u was just u naught. So all those factors combine, and you get this order of magnitude estimate. So what we learn is that this is some order 1 number. This is not particularly big. So nothing is interesting is happening in the location, in this capital U coordinate. The interesting thing is with the v, in which this is large. So r minus rs is actually very small because r minus rs, r of q minus rs is proportional to e to the v, which is equal to c over s black hole. So it's like a very, very small distance inside the apparent horizon. And so this says that QES is inside, but very close to the apparent horizon, to the black hole horizon. And this is also why its entropy follows, the downward page curve. So entropy follows the downward page curve. Part of the page curve, because essentially the downward part of the page curve follows the area of the slowly evaporating black hole. Okay, so all this sort of ties together very nicely, and we find a QES even in the evaporating black hole. So I will end by just one picture. Now, what we found is there is this singularity. We have this, and again, now I will draw I was drawing here the diamond corresponding to the black hole, but there is a diamond sort of corresponding to the radiation, which I've been drawing in blue, and sort of this entire interior part that sort of belongs to the radiation. So this is the entanglement wedge of the radiation, and this part is what we call the island. So blue is the radiation, entanglement wedge, the radiation. It equals the causal wedge plus the island. Okay, and let's emphasize why this S matter term is so important, right? As we have seen, Hawking radiation sets up entanglement between particles. If we have a particle A here, it has almost an EPR pair. It's an EPR partner A prime in the radiation. We have another B, there's like a B prime here. So, okay, so we have S gen is area plus S bulk, right? Or S matter. Okay, we can consider two things. So if you have no island, right? So the area of this point here, let's call this Q. You don't get any area because you didn't put the island, but you are penalized by S bulk because you have a contribution n log 2, where n is the number of these EPR pairs that you have obtained by Hawking radiation. And at late times, n is large, right? At late times. Okay, but if you do include the island, then you pay a penalty for the area. So it's the area at the point Q divided by G. And this is also big because G is small, so area over G is big. But since you included the EPR pairs together in your blue region, they contribute nothing to the entropy. So you get 0 here. So it's one or the other. And point is, at late times, this is small. Smaller at late times. So it wins out in the competition. And so this really underlies this entanglement structure that you set up a lot of entanglement between an interior region, which is very thin and skinny, and this radiation outside. Okay, thanks for listening. We'll stop here, and next time we'll do some toy examples of replica wormholes, like the derivation of this island rule and what we can say about that. Be tomorrow.
Thank you very much for the great lecture.
Thanks.
Please ask any questions. Can I ask one question about?
Yeah, please.
So here, qualitatively, I mean, previous eternal black hole, you have the extremal surface or island appear outside of the horizon,
Yeah.
but here inside the horizon. Can you intuitively explain the?
No, so actually, there are some arguments from this quantum focusing conjecture, which you might have thought would predict that this quantum extremal surface should always lie inside the horizon. Because what happens is a problem when if you have a quantum extremal surface and you start drawing such light rays that go parallel, there are some inequalities it has to satisfy. And if it becomes very big, so this falling into the singularity is okay. But if it makes it outside, it violates some quantum focusing conjectures. But what you have to realize is this
could
is
you
not a
explain
problem.
that it's focusing that some details
Yeah.
for student
Okay.
and
Maybe I can do that next time because it will take some time to explain it. But there is no contradiction actually. Even if you have the thing outside, it's not actually a problem. And one way to so that kind of logic does impose some constraints on the location of the quantum extremal surface. So for example, if you look at this equation that we had here, this equation that determines A star as a function of B. If you notice that A star has to be bigger than B because of positivity, the left-hand side is positive. So for the right-hand side to be positive, we must have A star bigger than B. So the condition of the quantum extremal surface being sort of behind the horizon, in this case, translates to this condition that A star has to be bigger than B. So that's sort of the most general constraint you can put on the system. But maybe I'll try to say some words about that next time. Explain some because I think it's
Okay, thank you.
Okay.
So any other question?
A question?
Yes.
Okay.
I mean, this island, sometimes it's outside the horizon, and sometimes it is located inside the horizon. And so what makes the difference?
Yeah, as I said, most of the island is actually inside the horizon. The difference is where the endpoint is whether this Q sort of lies slightly inside the horizon or slightly outside the horizon. And physically, there's not much difference because, being a Planckian distance inside or a Planckian distance outside doesn't make too much difference to the actual value of the entropy. But there are some inequalities that have to be obeyed. And those inequalities basically have to do with the Raychaudhuri equation. That would be the classical thing. And basically the quantum focusing conjecture is a quantum uplift of the Raychaudhuri equation. Something like that.
So you're gonna explain this quantum focusing conjecture?
Yeah, maybe next time I can say some words about it. Yeah.
Oh, okay.
Yeah, but there's no. I want to emphasize there's nothing very. Being this point Q being inside or outside, slightly inside or slightly outside, doesn't make much difference to the physical arguments that we have given.
Okay.
Yeah. What matters is that you capture all of these particles in your net. So you save on this n cost. So you don't pay this cost n. And there is actually ways to change the location of this Q. So imagine in this case, you start feeding the black hole, that the black hole is evaporating, but then as the black hole evaporates, you throw in another particle to make its mass exactly the same. And so you try to balance it. It's evaporating, but you throw in some thermal radiation. And what that does is moves this point Q towards the horizon. It moves it slowly outwards towards the horizon and sort of balances it. So at the point of this balance, which is slightly different than the eternal situations I've described, yes. So this gap here is controlled by, whether you throw in some stuff to slow down the evaporation rate of the black hole, for example. And so there is some physics in this gap. here. But from the point of view of just the page curve going up and down, it doesn't matter so much, but it matters for more finer information.
Okay, thanks.
Yeah.
Can I ask a question?
Yeah, please.
Could you give comments when the initial state is a largely mixed state, not a pure state?
Yeah, I can't. Do you have anything specific about that? I haven't thought much about that case.
Yeah, because the real
Yeah.
black hole is made from a largely mixed state, not a pure state.
Okay. But right. I would say that whatever it's entangled with, then we should include that as part of our radiation. Right. So if we make a black hole in a mixed state, it has some purifying system. And then we can just think of that system as a part of our radiation, right? And then the combined system is pure. So what you're saying is we have this page curve. Instead of starting the black hole here, we can start off here. That's fine. It's some starts in some mixed state. But as long as it is sort of less than maximally entangled, we can just imagine that this amount of entanglement was caused by some previously emitted Hawking radiation or something else. Yeah, I haven't done, for example, what I meant was I haven't done detailed computations in like JT gravity, if you have some mixed state and then what happens. But from the point of view of a qualitative prediction, this is what should happen. We can start off the black hole sort of here.
Well, I mean the equality of the radiation and black hole entropy is does not hold in the largely mixed initial state. So, so my question is related to the diagram, red and blue diagram in your previous slides.
Yeah. So let's say we have the black hole, right? And you say it's in a mixed state. So let's say, but mixed state just means there's a purifying auxiliary system, right? So let's say these two are in a pure state. And this auxiliary system might be some, CMB or something, whatever, or maybe some other black hole or I don't know, some planet or some star, could be anything. But the combined auxiliary system and the black hole is in some pure state. And now the black hole starts to emit some radiation, right? So what I'm saying is we should take the auxiliary plus radiation as the blue system.
Oh, I see. Okay.
Right. So then it doesn't matter.
Thanks.
Yeah.
So any other question? So here, for the evaporating case, what would be the final stage? It just you consider it back to the pure state, or what happened in the really?
You mean at the end?
At the end, yes.
Right. So at the end, we do get, because this quantum extremal surface is following the evaporating horizon, it will become very small. But at some point, the computation will break down because singularity is too close or something like that. So we don't know sort of what happens in this very end stage.
I see.
In detail. But we know, or what I mean is we can't compute the detailed form of this curve. But what I want to emphasize is that there was a paradox already at this point, right? Hawking predicted the answer would keep going up, and we managed to save this much of entropy. But what happens here is a matter of mystery. But I should say that, this is not the end of the road. So what is this page curve all about? The page curve is all about quantities like trace row, log row, right? Minus, or maybe if people have now computed these replica, trace row to the ends. But these are special objects, special combinations, or maybe I should not say special, too biased. These are just some combinations of row ij, right? Row is a matrix. It's a full, big, large matrix. And we haven't computed row ij for each I and j. Right? We only computed some overall sum, like we computed sum over ij, row ji. This is like trace row square. So the full out state, what the actual state of the Hawking radiation is, means what is its wave function or what is its density matrix, is in this object, is in the full matrix. But these guys are just some particular combinations of them. So all this replica wormhole quantum extremal surface doesn't give you, the fine-grained details of all the information there is in the Hawking radiation.
For
So
example, if you can calculate the row to the power n for all the n, is it possible to have some? Of course, you need a lot of n.
Yeah, let's say even if you computed it for n equals 1 through e to the s, so you knew, basically you would know still some combinations, right? Just because row is a matrix. And what the trace row to the n for all n would give you is the eigenvalues of that matrix.
Yes.
But let's say you're working in some simple spin, these are all just some spins, and you work in some simple basis. You still don't know what the unitary is that diagonalizes the matrix, right?
So you mean eigenvalue is not enough to understand some unitarity?
Yeah, because let's say you want to compute the matrix element of some spin operator, right? On like Hawking radiation is a bunch of qubits, and you want to compute like a 3-point function of some simple operator. Knowing the eigenvalues of rho is not enough. You also need to know the eigenvectors of rho, right? Because that's what the matrix element would determine. So there is information in the eigenvectors of rho, and that we don't get from this or any stuff that has been done in the past 2 years. So when people complain that, this is not the end of the Hawking, it's not the end of the story for information and so on and what the out state is, because we don't know what the final state is. We only managed to make the page curve consistent with unitarity, but there might be other things like the page curve that are still not consistent with unitarity.
Which is related to some low ij or some.
Yeah, exactly. Yeah. And all this gets related to this averaging stuff that people have talked about, because anyway, let me not go there now.
Any other question?
Yeah, I do. So
yes,
would I be right in thinking that one thing, the moment you have island formula, then basically if you can justify island formula and then everything else is a computation, so that's the non-trivial step. But once you have the island formula, then basically it says that page curve should turn out to be what you expect.
Yes.
However, so the difference would be, while earlier we would have calculated the entropy of radiation as just rho log rho, taking rho of Hawking. Here you're saying, no, it's not just the fine-grained entropy includes the island, and that's really the heart of the matter here. Would I be right in saying that?
Yes. Yeah, because we haven't computed rho ij, right? We haven't computed the fine-grained state. Just like in Ryu-Takayanagi, we don't first compute, like if we want to compute the entropy of some interval in a CFD2, in Ryu-Takayanagi, we don't first compute the density matrix of that interval and then trace rho log rho, right? We just say that there is gravity gives us a formula for computing just trace rho log rho in a box.
Well, I think we need the information of rho. For example, I think it's there because you would know what rho is because you're taking the CFT vacuum and then tracing over outside the interval. And on the gravity side, you're correspondingly taking ADS, right? You're not taking some other space-time. So otherwise, what entropy you're talking about? So here also, I think you have not explicitly shown that you know the elements, the matrix elements of rho, but I think it's implicit the moment you say we have Unruh vacuum and so on, then rho is known. It's basically Hawking rho.
Well, the Hawking rho is inconsistent with the answer, right? The Hawking rho has an entropy which is large at the end.
Exactly, but that's because you would have calculated the entropy, just simple the von Neumann entropy of Hawking's rho. But what you are computing now is not just von Neumann entropy of Hawking's rho, but that S bulk plus this island thing. You see, that's why I think that's a non-trivial, or at least to me, that seems like the heart of.
Yeah, I think I understand what you're saying, and this sort of in our paper from which all these examples are taken with Almheri and Maldacena, we tried to emphasize this. So there is a fundamental description of the system, which is, let's just do the zero temperature case, which is SYK plus the wire. Okay, and we can have here this is just a quantum mechanical description, no gravity, no nothing. You can put whatever complicated operator you want here, and you know what its description is. It's really, you just have some spin Hilbert space and you can do whatever you want.
Right.
On the gravity side, you're not so sure because this complicated object here, might have just been some simple object here. That what might be the picture of this complicated object. So it's not true that, I didn't emphasize this, I should have, that this flat space wing that we attach to the gravity diagram is not meant to be literally the same as the wire. It's again some code subspace. So the action on this side all happens in some code subspace of some simple operators defined, on top of this diagram that we are drawing here.
Right.
This is really the fundamental description of the system. So what I say when I say that we don't know rho ij is in this sense that, if you start, in some sense, on the right hand side, rho ij. If you just had some, let's say, tensor network evolving the state, the final state, you can compute it. But you don't compute it. There is no replica. There is no formula in gravity that computes that. There is no analog of the Ryu-Takenagi formula or the QES formula for rho ij. That would compute rho ij reliably. So it's a real difference. So that's why, I was saying to a question earlier, that this duality is not 100% derived, right? Because we know what the SYK is dual to. We sort of only guess what the SYK plus wire is dual to. But it will have these weird things that this complicated object on the right is just dual to some simple thing here.
Yeah.
Right. So in the paper, we use sort of bold-face notation for the objects on this side and the unbold notation for objects on this side.
Right.
So and the entropy that goes into the island, the S matter, is sort of the naive entropy that goes in. But yeah.
So bold radiation is not the same as unbold radiation, right?
Yeah. But the unbold radiation is just some stand-in intermediate thing that you use to compute these objects.
Yeah. So unbold. So unbold would be. So what I mean is unbold rho would be Hawking rho.
Yes. Yeah. That's right. But that's not what I meant here when I was saying find the row ij. This is
Yeah,
like
okay.
the bold
Yeah.
guy.
Sure.
Do you have a computation of the bold row ij from gravity?
No. So
Yeah, exactly. Yeah.
So, but given that the unbold row is Hawking row, if
Yeah.
the earlier, before all this work, one would just ask the question, well, what is the entropy of this? And you see it's increasing, increasing, increasing.
Yes.
But now you say,
Yes.
well, the fine-grained entropy that you should be computing is this Hawking row plus the island.
Yeah.
So it's
Yeah,
somehow fine-grained entropy. And that kind of solves the page curve.
Exactly. Yeah. That's exactly right. Yeah.
Okay. Okay. Yeah, I was just checking whether my understanding was right. Okay.
Yeah, no, you're right. So it's the fact that it's the fact that really it's that the operator algebras on a gravitating space-time like this are not just attached to causal diamonds. They're attached to these entanglement wedges.
Okay. Yeah.
Okay. Thanks for the discussion.
Well, thank you so very much for clarifying these things.
So, is there any question? If not, let's thanks speaker again.
Okay. Thanks so much, and
Thank you
see you
very
guys
much.
tomorrow.
Yeah, see you tomorrow.